After studying this module, you shall be able to know about the significance of conductometric type measurements, the basis of conductometry, the basics and applications of conductometric measurements. Analytical techniques based on electrochemical principles play an important role in the instrumental analytical chemistry. These methods are based on the electrical properties of a solution of an analyte when it is made part of an electrochemical cell. Electrochemical methods are often specific for particular oxidation state of an element. Instrumentation is inexpensive and they provide information about activities rather than the concentration of chemical species. For these methods, understanding is required for the basic theory and practical aspects of the operation of direct current electrochemical cells. Either current, resistance or voltage are measured on their own or in combination for different analytical purposes. Based on these measurements, there are various electroanalytical techniques that can again be classified into two categories: steady state and transient. Electron transfer reactions and diffusion transport are important for some, while they are unimportant for a few of the methods. Amongst electrochemical methodologies, measurement of electrochemical conductance is one of the oldest and simplest. The history of the development of conductive measurement dates back to as early as 18th century. Conductometry was developed by Andreas Baumgartner Friedrich Kohlrausch in 1860s. The first conductometric endpoint was found by Willis Whitney while he was studying the interactions of sulfuric acid and chromium sulfate complexes. Robert Berendt developed the first instrument for volumetric analysis in 1883, which allowed for testing the solubility of salts and hydrogen ion concentration as well as acid-base and redox titrations. The development of the glass electrode from 1909 onwards also helped to improve conductometric measurements. For conductometry and conductometric titrations, charge transport by migration is the basis. In conductometry, the progress of a chemical reaction is monitored by measuring the electrolytic conductance of the solution, which arises when the ions of an electrolyte transport charge, that is, conduct current through the bulk of a solution. Molecules of a solvent and solvated ions are continually colliding because of thermal energy and hence move in a random manner with frequent changes of speed and direction. The ions experience a force that attracts them towards the oppositely charged electrode on application of an electrical field to the solution. Now, we shall study about some of the general features. Conductance. The ability of a medium to carry electric current is known as conductance, and this is possible due to migration of ions under the influence of a potential gradient. For example, in wires of iron or copper, that is metallic conductors, electric current passes in the form of electron flow. But when electricity is passed through an electrolyte solution, positively charged ions migrate towards the cathode and negatively charged ions migrate to the anode. Hence, all ions present in the solution can carry the current. The movement of ions depend on their charge and size, the microscopic velocity of the medium, and the magnitude of the potential gradient. Also, Ohm's law is obeyed in a similar way as a metallic conductor as per the equation, that is, R equals to E by I, where E is the potential difference and I is the current intensity. The conductance is given by the reciprocal of the resistance, that is, G, which is the abbreviation for conductance, is equals to 1 by R. The units are ohm inverse or mhos or Siemens, where R is the resistance of the solution. The reciprocal of the resistance of a 1 cm tube of a liquid at a specified temperature is the specific conductance kappa, for which the unit is ohm inverse centimeter inverse or Siemens centimeter inverse. The conductance of the solution depends on various factors. Number 1, the temperature. It increases by increase of temperature, hence measurements need to be carried out at a constant temperature, as a slight increase of temperature even by 1 degree Celsius changes the conductance values. Number 2, the nature of the ions. The size, molecular weight, number of charges carried by the ion and certain other factors control the velocity by which the ions move towards the electrodes carrying the electric current, hence affecting the conductance values. Number 3 is the concentration of ions. The summation of contribution from all ions present gives the electrical conductance of a solution. The ionic concentration depends on the nature, implying that each of ion is independently presented, and also on the number per unit volume of the solution. The more the number of ions in solution, more is the conductance of the solution. Number 4 is the size of the electrode. The conductance varies with the cross-section area A and length L of a uniform conductor. It is directly proportional to A and inversely proportional to L. Hence, G equals to 1 by R equals to kappa A by D, or G into D by A equals to kappa, where D by A is capital K, which is the cell constant for a given cell with fixed electrodes. Capital K is a constant for a specific solution and changes if the concentration of the solution is changed. For conductance measurements, a cell is calibrated by measuring R when the cell contains a standard solution of known specific resistance, and then the cell constant is computed. As a solution of an electrolyte is diluted, the K, the cell constant, decreases, and hence kappa decreases as there are fewer ions to carry the electric current in each cubic centimeter of the solution. The electrode area should be large and the plates close together in solutions of low conductance. While for highly conducting solutions, the area of the electrodes should be small and the electrodes should be far apart. Now we shall discuss equivalent conductance lambda. The conductance of 1 gram equivalent of solute contained between the electrodes separated by a distance of 1 centimeter is the equivalent conductance. This expresses the ability of individual ions to conduct and is given by lambda, which is the equivalent conductance, equals to 1000 times kappa by C, where C is the concentration in gram equivalents per liter and volume of the solution is in cubic centimeters per equivalent, and that is equals to 1000 by C. Now we shall discuss equivalent ionic conductance. The electrical conductance of a solution is a summation of contributions from all the ions present and depends on the number of ions per unit volume of the solution and also on the velocity of ion with which it moves when the electromotive force is applied. At infinite dilution, interactions become nil. The ions theoretically are independent of one another and each ion contributes its part to the total conductance. Therefore, the overall conductance of the solution consists of sum of the individual equivalent ionic conductance of the cation and anion of the salt at infinite dilution. Other electrolytic measurements can then be used for measuring individual ionic conductance values. Hence, lambda infinity is equals to summation of lambda of cation plus summation lambda of anion, where lambda cation and lambda anion are the ionic conductances of the cations and anions respectively at infinite dilution. The values for the limiting ionic conductances for many ions in water at 25 degrees centigrade are available in reference handbooks. Now, we shall talk about the conductance measurements. In conductometric measurements, the electrodes are placed at intimate contact with the solution and an alternate potential is applied. Polarization at the surface of these electrodes is avoided by increasing the macroscopic surface area through platinization and or operation at sufficient high frequency. Under these conditions, the contribution of non-Faraday currents is so large that the electrode process is constant and assume the same for the bulk solution. As discussed earlier, the conductance is a reciprocal of resistance. So, to carry out conductometric measurement, one needs to measure the resistance of the solution. The instrument consists of two parts. Number 1 is the conductivity bridge, or called as the Coleridge bridge, a mean to measure the resistance and then convert it to conductivity unit. It consists of a Wheatstone bridge and an oscillator. Number 2 is the conductance cell, in which the solution to be measured and is filled. Commercially, various types of cells are available. The simplest to use is the dip cell for testing the liquid in an open container. It is merely immersed in the solution to a depth sufficient to cover the electrodes and the vent holes. A pair of individual platinum electrodes on glass wands is useful in conductance titrations. Pipette cells permits measurements with small volumes of solution as little as 0.01 ml in some designs. A conductance cell is calibrated by using a solution of known conductivity, usually a potassium chloride solution. For an operating frequency of 3000 Hz, any smooth metal surface can serve as an electrode. For industrial applications, stainless steel electrodes are used due to their desirable rigidity and low cost. In small cells where electrodes are close together, the cell constant is in fact not a constant but varies with concentration. Thus, for wide range measurements, a calibration is needed over the entire conductance range. Industrial flow cells with 3 electrodes are also used. Now, we shall see the conductance measurements. To eliminate the effect of Faraday process, measurements are made with an alternating current. If an alternating potential is applied, alternating current flows through the double layer capacitances at the 2 electrodes, and the resistance of the solution between them, including the inter-electrode capacitance in parallel with the cell. Each double layer capacitance provides such an easy path for alternating current that a potential cannot build up across the corresponding Faraday impedance to the point where Faraday current can flow. That is, the deposition potential is not exceeded. Platinizing the electrodes increases the double layer capacitance many-fold. Now, we shall see some of the analytical applications of conductometry. Direct or absolute measurements. This is used for checking purity of distilled water or other chemicals in industry, and also for the determination of physical constants like ionization constant. In this method, a series of standard solutions of extra pure grade of the substance to be determined is prepared. The conductivity is determined and a calibration curve is plotted representing conductivity against concentration. A solution of the substance to be tested is prepared and checked from the conductivity calibration curve. Second is the conductometric titrations. Conductometric titrations is a type of titration in which the electrolytic conductivity of the reaction mixture is continuously monitored as one reactant is added. The equivalent point is the point at which the conductivity undergoes a sudden change. The 2 highly conducting ions, namely hydroxyl and the hydrogen ions with a marked change in concentration, also result in the increase or decrease of the conductance associated with it. Here, it is the change of conductivity of the solution during the course of reaction which is important. The most important advantages of this method are that it can be used for the determination of turbid and highly colored solutions, very dilute solutions, reaction which is not complete and where there is no suitable indicator, for example, the reaction between a weak acid and a weak base. Another applications include high frequency titrations, measurement of dielectric constants, direct current conductivity analysis, etc. Practical applications include direct analysis, stream monitoring and conductometric titrations. Now, we shall summarize what we have learnt in this module. Among electrochemical methodologies, measurement of electrochemical conductance is one of the oldest and simplest. The ability of a medium to carry electric current is known as conductance, and this is possible due to the migration of ions under the influence of a potential gradient. The progress of a chemical reaction in conductometry is monitored by measuring the electrolytic conductance of the solution. The electrical conductance of a solution is a summation of contributions from all the ions present and depend on the number of ions per unit volume of the solution. and also on the velocities with which these ions move under the influence of the applied electromotive force. The conductance of the solution depends on various factors like temperature, nature of ions, concentration of ions, size of the electrodes, etc. Accurate results can be obtained by conductometry. It gives a sharp endpoint in every case. Apparatus use is not sophisticated. However, the disadvantage is the high temperature dependence of conductance. High salt levels and high concentration of ions sometimes mask the conductivity and hence do not give accurate results. Analytical applications include direct or absolute analysis, stream monitoring, and conductometric titrations. Conductometric titration is a type of titration in which the electrolytic conductivity of the reaction mixture is continuously monitored as one of the reactant is added. The equivalence point is the point at which the conductivity undergoes a sudden change. Conductometric titration works for dilute as well as colored solutions. It is suitable for both weak base as well as weak acid and also for turbid solutions, and can be used even when there is no suitable indicator. Conductometric titrations has many applications, that is, it can be used for acid-base titrations, redox titrations, precipitation titrations and complexometric titrations.